Okay, so let's get started. We're going to look at one more numerical technique, so to speak. After this lecture, from the next lecture on, we're going to look more in detail into performance and how to get more performance out of your code. But this is still the last one of a numerical technique that is implemented already for you, and you don't have to worry about it, and so you should know about it. And it all revolves about randomness, around randomness. So we're going to look at randomness and how to make it and why you would want it, and we'll look at an application of randomness in scientific computing. Now, randomness might not seem particularly scientific. So when would you need randomness in your simulation or in your analysis? Sometimes that's because that's exactly what you want to study. You might have some physical phenomena that actually does have noise, like Brownian motion or noise in an electric circuit, microscopic noise it's called. So your description might actually involve noise, might involve randomness. And so then you, of course, want that in your simulation if that's what you're trying to simulate. But there's other cases where this is very useful. For instance, when we looked at our integration, we saw that it can be hard to do this for many degrees of freedom. If you're doing a statistical physics average, canonical average, in other words, if you want to know how microscopic interactions lead to macroscopic properties, that's what you do. The number of degrees of freedom is of the order of 10 to the 23rd, and that's just not doable with anything but some sort of sampling. You won't do that, but you will not at that scale. But you'll need a lot of possibilities to sample, and you can't sample them on all. You're going to sample them randomly, and it turns out that that's a more efficient way to try and do this. The point there is to get a converged answer, so to get an average out, and to do that average rather than trying to find every possible point in your curve, just sort of randomly hope that you'll get all the important parts. You might also be doing some sort of data analysis. You might have a technique that assumes a certain randomness in your data. And if you wanted to test whether your statistical approach is any good, you'd probably want to feed it some sort of fake random data. So again, there you're kind of in the situation where you want to model randomness. So we want randomness in our scientific computing, but computers are fairly deterministic. So maybe we don't do it with a computer. Maybe we get it from somewhere else. So here are some real random number generators. Turns out lava lamps are fairly good randomness generators. So you can't quite know where it's going at any given time. Radioactive decay is a very good random number generator. It's still dangerous, but other quantum processes too. Atmospheric noise you could use as randomness. You could use so that's all sort of external, and some of it a bit hard to get to. But your computer hardware itself has noise as well. This could be thermal noise. It could also be, if your computer is connected to a network, it could use the network traffic, which is kind of random. I mean, who knows what you're looking at on the net? Depends. That can be used to generate randomness. But what all of these have in common, apart from being really random, is that it's generally slow. Like you don't get your next random number until something has happened, right? So until the lava lamp has turned around, or your barren atom has decayed, or it's also impossible to reproduce. And that is another thing that, for scientific purposes, is actually annoying. You want randomness, but at the same time, you would want the same randomness over and over and over and over again, because suppose that something's wrong in your program, it's not quite working. You run it again. If your randomness is different, now it might suddenly happen to work, right? So you can't really you have to be able to control this randomness, and none of these real ones have that. Another thing that is maybe even more serious is that it's hard to characterize what the distribution is. Okay. So what do we do instead? we have pseudo random number generators. We come up with an algorithm that produces random numbers. That by itself is just plain impossible. If it's an algorithm, if it's deterministic, it's not random. So we want some sequence of numbers that looks random. Right? So it only has to act random. It has to be random enough and to give us a fair and uncorrelated sequence of numbers. So all of these random number generators, these pseudo-random number generators, work the same way with different levels of sophistication. They have some sort of state, some set of numbers or a single number that they hold in memory, from which they produce a number, and from which they produce the next state. So they go from state to state, and each state corresponds to a number. And the advancements of the states are deterministic. So there's a prescription that says, from this state, I get to that state. That deterministicness means that I can actually control or reproduce the same sequence when I want to, as long as my starting state, so my starting seed, is the same. And if I have my my advanced algorithm chosen properly, I can even control what kind of distribution that I would get. Right? And so as long as these numbers that are produced are independent and identically distributed according to some predefined distribution, usually something uniform between, say, 0 and 1, then that's all we care about. But these are kind of strong things, because if the state proceeds deterministically, getting subsequent numbers to be independent is strictly never possible. So it just has to kind of look that way. To have them all be identical distributed might be easier if you do it this well, and uniform similarly. Okay, so we're going to try and to see how this would work. But if this isn't satisfied, they aren't random enough. So it depends a lot on your algorithm, and you basically have to test whether this is true. So I created a tiny little class that produces random numbers. So we haven't done much object-oriented programming. It doesn't really matter too much what this is, that this is an object. Here's our state. So this class holds on to a state, just a single integer. And when I started, I gave it a seed, and the seed just becomes the value of the state. So that's some integer. And I want this to produce random plus ones or minus ones, representing the toss of a coin. So the way I'm going to do that is I'm going to see if the state is an even number, and if it's an even number, it's going to be 1, and if the state is not, it's going to be minus 1. Right? So this gives me 0 or 1, and so what is returned gives me minus 1 or plus 1. And the way the state is progressed is pretty much the simplest way I could do anything is to do state plus plus. So I add 1 to the state. So if I start with a seed of 13, that's odd. So this gives me minus 1. My toss gives me minus 1. The next state is 14. It will give me a heads up. This is how I could use this. So suppose that this coin is in the header file bad coin. I create the bad coin, and I started with a seed of 13. I'm in the habit of giving seeds that are unlucky, so 13 is it's my favorite random seed. And I'm going to toss the coin 20 times, and I'm going to print out what it is, so plus or minus 1. The concept means that makes sense? Yeah. So let's see what that does, whether it's fair, and whether the samples are independent. Those are going to be our two main concerns. So we're going to draw n samples. We had 20 in the example, and we'll look at two tests. First, fairness, where we're just counting each of the values. So the value here is plus or minus 1. So I'm just counting how many of my xi, so the xi is my series of values, plus or minus 1. I'm going to see how many of them are 1 and how many are plus or minus 1. So I'm just counting. It's just a histogram. If it's fair, then c plus 1 and c minus 1 should be roughly the same, right? And independence I'm going to do by looking at a correlation function. So I'm going to see how the value at I, and at I plus j in the sequence, so that's the jth number after it, how they're correlated, and I'm just defining that by subtracting the average, which in this case should be 0, but subtract the average of each of the samples. I multiply the ones that are j apart, and then I sum over all of the samples and average that. Now, the reason I do this is that if these are truly independent from one another, there by chance will be cases where the next toss will be 1, even if the previous was 1. That's fine, but on average what you would expect if you have n samples is that for any j bigger than 0, that is to say when you're not counting the correlation of a coin toss with itself, so two different ones, they should be uncorrelated. What you would find is that this value, this quantity should be of order 1 over the square root of the number of samples. So that's something we can test. So we have fairness by a histogram and independence by a correlation between subsequent samples. So let's look for our test here. So what if I have 50? This is the fairness. So this is my histogram of the numbers that come out of that example. And this is perfectly fair. But there's an equal number of negative ones and plus ones, equal ones of heads and tails. It's a very fair coin. How about independence? Well, here's the correlation function. Now, the correlation of a value with itself is always 1 if it's properly normalized. And so it should start at 1, and then the rest should be of order squared, 1 over square root n. But instead we get this zigzag. It's -1 plus 1, -1 plus 1. So this is constantly correlated or anti-correlated with itself. This is actually a sequence of +1, -1, +1, -1, +1, -1, +1. That is fair, but absolutely not random. Okay. And that's exactly why we get this perfectly correlated or anti-correlated. So how do we fix this? Well, we can try and come up with a better way to change the state. So the same algorithm except for how I change the state, and I just chose something. I don't even know if this comes out of nowhere. We're saying, well, it's getting more complicated. It has to not give me plus or minus 1. So let me take the sign of the state and multiply it by 100 and add 100, and that's the new state. And I have no idea what that does. And then still return -1 or +1. In other words, I made a random change. See if that made it really random. So here's the fairness estimate. So I did the same 20 samples. It's not very fair, but it's not very bad either. And then the independence, well, here's what I got. It started at 1, and then it sort of oscillates a little bit. It's 20, so 1 over square root 20. Then maybe that's better. It's not as bad as before, but that is only 20 samples. So yeah, sorry. So the output is so let's look at the code one more time then. So the output is either plus or minus 1, right? So I have two states, but the state itself is an integer. So in this first case, it just goes from 0 to 20 because I had 20 samples. In this case, it goes to 20 iterations. So the state is not plus or minus 1. The state is some internal representation that can have more information than just the outcome. Yeah, good point. So that's going to be the secret sauce in the end. There's more than we see. So let's see if this is really much better by looking at a larger sample. So let's take 200 samples. Here's our fairness test. Well, that's horrendous. I didn't try when I came up with that recipe to make this fair, so that the fact that it's not fair is maybe not so surprising. But let's see if the independence is any better. And it's not. So I still have lots of correlations. I was just looking at the first 20, and it turns out, well, that there's some sort of decay of the correlations, but then they come back. And that's not surprising. I had a sign in there. Obviously, it's going to be some correlation. So the moral of the story is don't do this yourself. Like, you can try and come up with this stuff. It's just, it won't be very good unless you really know what you're doing, which means that you are a researcher of random number generators, in which case you're probably not here. So we're going to use the research that has been done. But we want to make sure that they do a few things well. They give you the distribution you want, uniform or Gaussian or normal. You want them to be unpredictable, reproducible, generated quickly. It shouldn't take too long. If it takes longer than actually looking at the radioactive process, then we might as well do that. And have to have what's called a long period. Because this is deterministic, there is an internal variable or set of variables at that state that eventually will return to the same state. If I had my integer that's 32 bits, it means that I can only have 4 billion possible values. So after 4 billion values, I am sure that I'll return to the same set. Most algorithms are worse than that, and they return to the same set of values. They repeat the same set of values after a shorter period. So we want this period of our random number generator to be long. Okay. So you used to have to do this yourself, but no, not anymore. And even there used to be good libraries for this stuff. There still are. You might use them. But even C++11 itself, in the standard, has a couple of random number generators that are fairly decent. So here's using C++ random number generators in the header file called random. And it does it a slightly confusing way the first time around. But that's because in this library, or this standard library called random, it separates the engine, which means the generation of the state and the advancement of the state, from the distribution that you want to have. So I can have any engine create some sort of internal state that evolves more or less randomly, although not really. And then I can put on top of that any sort of transformation that makes that internal state into a set of values that is, in this case, uniform distributed. So I have my engine, that is in this case called MT199937, and I have my uniform distribution of integers. Those are together my state here, and other than that, it works very similarly because I'm using everything that's already implemented. I give the engine a seed, and when I want to toss a coin, I'm asking for a uniform distribution that gives me the state, and then since the state gives me an integer, and I want to sort of get that integer to be it gives me plus or minus 1 back again, so that's what this is. So I'm wrapping random integers into something that gives me plus or minus 1. Here are the tests. It's fairly fair. The difference between here is actually randomness that you should expect, but especially the correlations are very, very nice. So I see this starting at 1 and dropping down to something that is of the order of 1 over square root 200. That's the kind of independence you'd want to see.
This rand 100.
Well, this is so it's your responsibility to know what it really does.
Oh.
There are some really, really bad standard random number generators. C used to come with a random number generator called rand. That is basically no good. You don't want to use this for production. Now, if you just generate it, if it's sort of an example, or you just need it, sure, right? But anything that relies on the randomness, anything that has a substantial number of points to be drawn, you want to know what is this random number generator really, really doing. And so, and if you don't know it, if it doesn't say, you should do some tests and see if the best tests, if you don't know, you just but if you have more than one random number generator at your disposal, is to run the same thing again with 2 random numbers, 2 different random number generators. And if you get different results from the 2, at least one of them is wrong. Right? Now we need a third one. If they're both sort of the same, you say, well, that gives me some level of confidence, right? And that's the minimum you should do. You should actually never use a single random number generator if you want to be really sure of your results. There's some other tests, but I won't go into them too much. You can look at the moments and see if they give you the distribution that you expect. You can do fancier things like look at the spacings between subsequent points to see if they're Poisson. You could look at all possible ways of drawing 5 numbers. There's 120 ways to do that. See if they all get there. You could play all kind of games. There's the whole toolkit here if you wanted to check it out, just to sort of really put your number generator at a through the ringer. But since this is still the part of the course where we tell you not to code it yourself, what is out there? What are some good ones? Just sort of as a rule of thumb. You'd still want to do your test. You still want to make sure that you use 2 of them and see you get the same results. But here's a few decent ones. So they come with fancy names because these are evolving things, and I'm sure there was an R1 once, but there's now R1279. That is a nice so-called lagged Fibonacci generator. I won't go into what that means. The Mersenne twister is very popular. You find it in almost any standard random number generator. And so you find it in C++ as standard. You'll find it in Python. You'll find it in R. It is decent, and it's not too slow. There's some other ones that might not be in the standard, but they're good. There's a well generator, which is in my LaTeX, which is developed at Montreal. But there's some known bad ones as well. And if you just want to see how bad your stuff could get, you might just want to pick that and see, okay, how poor is this? This is a bad version of the first one. Almost anything in numerical recipes isn't particularly good. It's good for demonstration purposes and to get an idea. It has short periods, so it'll repeat itself quickly. It'll tend to be slow. And it often sort of spectacularly fails these statistical tests. You don't really want to do it. It's good. I like numerical recipes as a learning book, but not necessarily as a you don't want to use every recipe as is. I definitely don't stick to the standard Unix generators like Rand or drand48. They have short periods and correlations, and that's generally not the way to go. So you noticed in the example that I actually chose the Mersenne twister. There is a default as well. So in the C++ standard, you can use the default engine, and it won't tell you what it is. It's implementation defined, which wouldn't be so bad if the implementation told you what it actually was, but it won't tell you. So don't use that. You need to know what random number generator you were using. Your referees are going to ask if the stuff looks suspicious, and you submit your paper. They will say, "What random number generator did you use?" And you say, "The default." Well, that's not an answer, right? So know what you're doing, and that's why you should always just sort of specifically say, "I want this particular one."
Twister is the one in Python.
I don't know if it's the default there. I have to look that up, but it's certainly in there. Do you know, Marcelo, what the defaults are? But I do know that they are. You can specifically request them as well, and that's good. Yeah.
That's the statistics on that.
Yeah, I guess so. But you still don't have an answer for what it's really doing. So better not to, because somebody will ask and say, "I don't know," and that's You could say the best you could do in that case. Suppose that it's been a lot of work and you've had many months of calculations. You'd have to specify exactly what version of the compiler you were using, what version of the library, and then somebody could dig in and figure out what it was actually at. But just saying it's just the default will not. It's not so scientific. So that's the idea about random number generators. I showed you some bad ones, but I give you an idea of what goes on under the hood, and some good ones that you just use. There are better ones than Mersenne twister. There's people that are even complaining about that one, and then with reason. But basically, you test one against the other, and that's how I used to do it. And I say, okay, they gave the same answer. Okay, they don't give the same answer. I have to try and come up with a better way, or a better one. So let's look at applications of random numbers in scientific computing. And in particular, let's look at Monte Carlo and Monte Carlo simulations. This is the way that I used to do a lot of my Monte Carlo simulations, which were really after computing an integral. with some distribution P. X was my space of configurations, and A is whatever I wanted to compute. But my X had at least a dimensionality of 3,000 or 3 million or something like that. So doing this integral for real is just not doable. And this is typically for doing any sort of statistical mechanics average. But it's not the only situation where you get this. So generally, when you do Monte Carlo analysis, it has a very broad meaning. It basically means any analysis that you add some randomness to. And of course, Monte Carlo, you can imagine, comes from the casino connotation. But you want to get these values X. You want to get a sample of them. So you can't get every possible point in your integral or interval of interest or your domain of interest. You want a sample. You want some of them, a lot of them. Right? You want probably billions, but at least millions. But there's no way you sample everything. So you want to draw them from the distribution function P in such a way that you basically get the most important ones. Right? So if I do that, then all I have to do is take all these values X that I chose from this distribution P, compute A at those points X, and simply average it. I don't have to multiply by Px anymore because I draw them from that distribution P. Okay, so that's typically what you're after. You know the distribution of points, you draw from it, and you just average the values of A on that point. That's what you do. Okay. Obviously, this only works if you have a good random number generator. So you have the two things. You have the probability distribution function, you need your randomness, and then the rest is more or less trivial. You can check for convergence by taking more and more points, more and more samples. So that's a nice controlled experiment if you want. And that's kind of what you do.
So it's like particles?
X could be positions of particles. So say I have 100 particles in 2 dimensions, that's 200 numbers. That's a 200-dimensional space. Right? If I want to do a regular grid in that space, even if it's confined in a box, and they have 100 points in each direction, that's 100 to the 200th points. And that's why it becomes impractical. And that is a small case. So you're going to try and do something else. So I have a few examples. Just to give you an idea, I have many more, but I don't want to spend all time just explaining that. But here's an example that isn't necessarily just physical science or physics. You can do this kind of applications to almost any field. You can do it to finance. You can do it to traffic flow. So here's a traffic flow example. And there's a model named after Nagel and Schreckenberg. It's a 1D toy model to see how you can get traffic and how you can get things like traffic jams and stuff like that. So we imagine we have a bunch of cars on a road, but the road is discrete, so you hop from one spot to the other. And the cars have a velocity. And this is what the prescription is. If your car's velocity is below the maximum velocity, you speed up. Nobody wants to drive below the speed. And so you always try to speed up. Now, of course, if there's a car in front of you and the car is a distance d away, if you increase your speed by more than that velocity, you would hit the car. So you're not going to do that. So you're going to slow down and reduce your velocity such that you don't hit the car in front of you. And then the last part is you add some randomness. And you say, whenever the speed is bigger than 0, there's some probability that I reduce my speed. I take my foot off the gas a little bit by accident, or I'm distracted. These things happen. And at every move, the car moves ahead by the number of steps that there are. You're going to put this on a circular track just to have some sort of, not to have to worry about boundary conditions. And you can see what happens. So you put your cars there, they have some velocity, you have these rules. The velocity changes, it goes up, or is the maximum. There is a maximum of how far away you are from the next one. And then here is your randomness. You decelerate with the probability p, and every time you change your position of the part of the car. So this is an example of a Monte Carlo simulation because there's a probability involved. I've plotted here the outcome of such a simulation. I forgot the exact parameters because they're on the bottom and they fell off. They're right here. In any case, it looks like we have a road of about 1,000 steps. You can guess that we have about, I say, 25% covered in cars. Here's the time. So initially we have just a whole bunch of cars, and sometimes you can see that the cars aren't moving much. And these are my traffic jams. You can also see the traffic jams go backwards, and that tends to be how traffic jams propagate. This is why if you're in a traffic jam and you get out of it, you can't see where the accident was, because the accident happened here, but this has already been cleared, and you're just over here and you will never see it. There's some vague analogy with special relativity, but in any case, this is your light cone. I mean, this is your traffic jam. And it gives so it's now if you have no randomness, what will happen is these guys either are completely stuck or they're not, and so you don't get this dynamic. You either start with a situation that is jammed or not, and so this randomness is kind of important to be realistic. And jams happen spontaneously in this model, and jams will eventually get resolved. There's an important part here in this Monte Carlo, that is, we're trying to do a step with a certain probability. And I want to kind of explain how you do that, because that's at the essence of doing Monte Carlo simulations. You want to try something with a certain probability. How do you do that? And so this is how you do that. Once you've seen it once, it's pretty easy to see. So you might want to do this. How do you know if you really want to do it? Well, you draw a random number, R, using some pseudo-random number generator with a uniform distribution between 0 and 1. And since p is also between 0 and 1, what we're going to do is we're going to check if that random number is less than p. The chance that it is less than p is exactly p. You might need to think of that for a second, but I choose a random number between 0 and 1. The chance that it is between 0 and p is p. So if it's less than p, if that r is less than p, we'll accept this move, this trial move, and we'll do it. Otherwise, we won't do it. So that's what it means to say, I take this step with a probability p, and this is how we can use a random number generator to do that. Right? If r is greater than p, we leave it as it is. So our next state is exactly the same as our p. We don't always do something. In this case, we did it with every car, so there tends to be always some car that is moving. Does this make sense? So this is the simplest case because there's just, it happens with a certain probability p that's always the same, that is constant. I want to look at one more example. Which gets a little bit closer to physics. We can look at molecular motion or particle motion. So we can consider a simple dynamics of molecules. I like to call them molecules, but they could be any kind of particle. Where we're trying to do this. So we can randomly perturb the position of a molecule. And we can then see what effect that has on the energy of the system. So typically, a bunch of molecules, given their configuration, will give you a certain energy. You change the configuration, you change the position, you change the energy. Usually that's the sum of our pairwise potentials. We talked about MD a little bit. That's what it is. Now, if the energy goes down, we're going to say we like that. So we're going to keep that new position. That would be a way to try and do minimization. Right? So we can try and find the lowest energy. You would keep going down sort of randomly. But in this case, that's not the only possibility. Because if the energy of the system would go up by this perturbation, I'm still going to allow it with a certain probability. And the probability is going to be the exponent of minus the difference of energy over T, where T is the temperature. If you're concerned with units, that T should be kBT, so the Boltzmann constant T. So R here again is this random number between 0 and 1, and T is a temperature. So if this is true, then this must simulate a set of molecules at that given temperature T. So we can imagine a container, a bunch of molecules held at a certain temperature T. And you can actually show if you do this for all molecules and for a couple of time steps, that the distribution of configurations you get is exactly the distribution of configurations that matches that temperature. So the canonical distribution of that state is explored by doing exactly these rules. If I only went down, I would slowly get into probably a local minimum. But if I have a higher temperature, then I can explore different configurations. So this is a typical molecular Monte Carlo model. So I'm going to show you an example that I took up. It's easy to make boring ones. So this is my first attempt at not being boring with the particles. It's still a little bit boring. So I imagine I have a bunch of particles in a spherical shell or a circle, because it's easier to plot. So I just plot them somewhere. I think I had 100 or 200 particles, and I have them fall down with this dynamics of doing random steps. And the way they fall down is through gravity. That's a potential. That's an energy. And the way they stay in the shell is that there's a rather large energy for them to try and go into the shell. So that gives you a large delta E. And if delta E is large, it's very unlikely that they get into that shell. And then I put a hole at the bottom. That's the part that makes it a little bit more interesting. So this is my starting point. T equals 0. I have my spherical shell, and this little inner shell is where I started all my points. There's a hole in the bottom. They can't go through the floor, and they'll fall down. Somewhere here I had a movie of that. So here they go. They fall. I went pretty quickly. It started at the beginning. So initially they're pretty fast. And some of them escape. Oops, as soon as I move, that thing goes there. And as I said, it's not as mind-blowing as I thought it would be. But they fall down through gravity, they get stuck here, and they escape. So I could try and do things like figure out how long it takes them to escape, depending on the size of the hole that I put in. There's a bunch of parameters that you need. So here was my end result after 1,000 steps. Now you could be fancy and say, well, this is obviously a cell, and these are chemicals in the cell they're trying to escape, or these are viruses, and you can make this into a biophysics application. Maybe that would be true. But I want to say that this is cute and nice, but be aware. This is fake, right? This is fake dynamics. This isn't real. The only constraint that we put on this set of rules is that it gives us the distribution of an equilibrium system at a given temperature. That's what we did. This isn't equilibrium. This isn't necessarily how molecules really move. So this is a very good way to look at equilibrium and steady state properties. It is a questionable way to look at dynamics at molecular scales. Molecules don't move random. They move fairly regularly. At a larger scale, it might look random, but that's a different issue. So now there's cases where this is a decent model. When your particles are large and immersed in some sort of fluid, they kind of move like this. They have Brownian motion. And then it's not the worst model. But if that's not what you have, this is not your approach. So in the end of the day, you want to simulate the model that you have, not something that is nice and cute. Now, that is all the bad stuff about, or not the bad stuff, but the warning stuff about molecular Monte Carlo. It's more of a sampling method than a dynamics method. But since that dynamics is artificial, it doesn't even have to look real. This kind of looks real, like if this was a fluid, and these were some particles in the fluid, and there was a leak. Yeah, this could happen. This is not strange, right? But if it isn't, then it's strange. The molecule is going to go in straight lines because it has nothing to hit against if it's just a vacuum. That's not what this thing does. But what this can do is you can add anything else to the dynamics. If it's artificial anyway, you can put all kinds of tweaks in that allow these particles to maybe jump from the top all the way to the bottom. You don't care as long as you have for every step the same rule that you accept it depending on the energy difference. And the reason that these kind of steps can become important is that it might actually be very hard for the system to find this little hole. Right? So you spend a long time trying to get these particles in here, whereas you just want to sample all possible configurations. So by just putting them down here as an arbitrary step, you can speed up your sampling problem and just say, well, that's fine as long as I weigh it correctly. So there's an art in here. There's some different techniques you can use where you can steer your Monte Carlo, but it makes the dynamics even less real. Right? So don't count on this to tell you anymore how fast my particles can escape if I allow them to just jump straight through the wall. Then that's it. But if I just want to know what kind of configurations are possible, say I want to know all kinds of properties of how things pack within the shell while it's depleting, that could be a question they can answer. Okay? Questions?
Macro model.
Yeah, so it all depends on what you're after. Like you might not know the equation of state. This might be a way to get it, right? So it all depends. If you know things like equation of state, how your viscosities change with temperature and pressure, you could go on a higher level. You could just basically do hydrodynamics, and maybe you have hydrodynamics with tracer particles in it. Again, that's so. If you know those properties, yeah, you're not going to do it this way. You shouldn't. It's too expensive. But it's when you want to know something based on the microscopics, or suppose I have these rules, and that's kind of the game you play with this traffic flow, right? These are of course not really how we drive our cars, but there's some semblance of what you might do, and you could tweak it. So it's more of an what if, and this what this model already shows is that jams can be expected to travel backwards. It is counterintuitive. It's not strange, but it's counterintuitive, and a simple model can show you that already. So that's it only derives from the individual's behavior. So I can try and tweak the individual. Suppose that I had 2 lanes. Suppose that some people are really slow drivers, or suppose there's some people that are really speeding. What happens, right? I could try putting collisions. So I can play that game. Not trying to be too close to reality, but still getting insight in sort of the general trend of how systems behave. Research. Okay?